So I'm going to mostly talk, you can interrupt me if you want, but mostly I'm going to talk a little bit about what students have figured out in this pattern over the last few days. Because I just want to kind of put it all together. A lot of people have figured it out, but not everyone, it's not making sense to everyone quite, I don't think. So this is the method. I think everyone sees the screen right now, right? This is Vivian's method of counting the tiles in this visual pattern we've been looking at. So as you've all talked about, what Vivian saw was one red tile on the left side. I mean, I colored it red, but she saw one tile on the left side, and then she saw groups of 4 tiles, which I've made green, right? She saw in the first figure, she saw one red tile and then one group of 4 green tiles. And then in figure 2, she saw one red tile and 2 groups of 4 tiles. And then figure 3, one red tile and 3 groups of 4 tiles. And then she said, well, figure 4 is going to be one red tile and 4 groups of green tiles, right? So we can start to write this in words like this, right? So figure 1 is one red tile and one group of 4 tiles. Figure 2 is one red tile and 2 groups of 4 green tiles. Figure 3 is one red tile plus 3 groups of 4 green tiles. So if we wanted to jump ahead, because a lot of this is about predicting like what happens with any old number we put in here, right? So what about figure 10? We don't want to draw it. It's going to be, and we could, but it's going to take, if we draw it, it'll be fine. But it'll take us a while, right? So maybe we don't need to draw it because we can say it's going to be one red tile plus 10 groups of 4 green tiles. Right, so we're going to see that same little group of 4 10 times plus the one red one on the left side. What about figure 100? I definitely don't want to draw that. One red tile plus 100 groups, right? That's that same 4 tiles. I mean, we're going to have many, many different shades of green or whatever, but it's going to be the same 4, but 100 groups of 4, right? So then my question to you all is, what's changing? When you look at this whole situation, what is changing?
The group.
So who is that? That was Cornelia?
Yes.
So what do you mean when you say the groups?
Keep on.
She's counting each time she adds up, she just has the amount of groups she has, but the one red tile still remains and the amount of green tiles still remains.
So the thing that's changing is what?
The number of groups.
The number of groups is changing. The other stuff is not changing. So could Cornelia help us see that? Is there anything else that you see that's changing when you think about this whole situation? I see one other thing that's changing.
Can I say something?
Sure, Malia, go ahead.
I see that every group have four extra more. You know, the first one was one red tie and 4 1 groups. The second one was one red tie and 2 4 groups. So each group have increased it 4.
Yeah, so as you go up by 1 figure number, you get an extra 4 tiles.
Yes.
Yeah, for sure. Anything else that you all see changing in this whole situation? Everyone, the number of groups is changing. Anything else? Maybe it's too obvious.
The total amount of tiles.
That's true. The total number of tiles is absolutely changing, right? Yeah, and it's not even shown here. We don't even see the total number. But so the total, yeah, that's a really good point. So I'm going to put the number of groups and the total number of tiles is absolutely changing. One other thing that's changing, and I think maybe it's just obvious, is maybe why you're not saying it, is the figure number is changing. Right? So over here, let me move this. Stuff is changing. So the figure number is changing, right? Figure 1, then figure 2, then figure 3, now figure 10, figure 100. That's changing as well, right? The figure number is changing and the number of groups is changing and the total number of tiles is changing, which is a really good point. I hadn't even thought about that. So now, what's staying the same?
Red tiles.
Give myself enough room here. Say it again.
The one red tile have not changed.
Right, so I'm trying to figure out which color to choose here. Let me see here. Okay, so the one red tile is staying the same. It's not changing.
Yeah.
What else? What else isn't changing?
The 4 green tiles.
The lighter green tile has not changed.
What do you mean? There's like 4 in the first one, there's 8 in the second one, there's 12 in the third one. What do you mean? What do you mean it's not changing?
Because
to me, this. Okay.
Go ahead, Cyrus. Yeah.
The 4 green tiles is not changing.
The 4 green tiles, but what do you mean? What about the 4 green tiles?
Okay, there's a group, the group of 4 green tiles. They don't change. They keep increasing.
The light ones?
the light ones.
All of them, all greens.
No, the light ones.
The light green tile.
You're saying, oh, there's the same, the light one is always there.
Always
Yeah, none of them changes. They keep increasing.
So Cyrus, what do you mean when you say none of them are changing? Because there's more.
Because every time you, for example, in figure 1, right, there's 4 green tiles, right? So in the second figure, we add another 4 green tiles. And then the third one, we add an extra 4 tiles so we can continue.
So we keep on adding 4 tiles all the time at the end.
So they increase it.
It's always 4 green tiles. So I would say it's not that the 4 green tiles aren't changing, it's that the number in the group is always 4. Because we know the total number of groups is changing, right? There's 1 group of 4, there's 2 groups of 4, there's 3 groups of 4, but it's always 4 in the group, right? That's not changing. Okay, so what we're trying to do though, is we're trying to figure out how to make a prediction for any number, right? So we looked at 10, we looked at 100. What about X? Because a figure X is any number, right? We could put any number in. So what would we do?
1 red tile plus X group of 4 green tiles.
1 red tile plus X groups of 4 green tiles. Whoops, wrong color. So X is the thing that's changing, right?
Mm-hmm.
X is by the way, is the variable, right? Which is related to the word vary, which means change, right? So they call X a variable because it's representing, it's representing a quantity that changes in this case, right? It could be 5, it could be 10, it could be 1,000, right? X varies, it's a variable, right? The 1 red tile actually is an example of a constant. The constant meaning it doesn't change. So sometimes you'll see these words in algebra where they talk about variables and constants. A constant is something that doesn't change. A variable is something that does change, right? But you already understand that the red tile doesn't change. It's always there. And that the number of groups is changing. So that's why we use X, a variable. So what you have here, the 1 red tile plus X groups of 4 green tiles, is an algebraic rule in words. This is a perfectly good algebraic rule. It works for any number or any figure number. So it doesn't matter. Figure 5 million, you guys could figure out how many tiles it would be in there, right? We might need a computer to draw it, but you guys could all figure it out, right? So that's perfectly fine. But we also want to be able to express it as an equation using symbols, right? And understand those symbols, right? So let me clear and move on to the next screen. So we're going to kind of do the same thing here, but this time we're using a table, right? This is a function table, as some people have called it. It's a way of understanding algebraic patterns. The tables are used quite often, and then they're used to make graphs later. So using Vivian's method, you all have created tables and made expressions. And so this expression means the same thing as the other thing you did, right? One red tile plus one group of 4 green tiles, right? 1 plus one group of 4. That's what this means. 1 plus 1 times 4. You may have not seen this asterisk used as a multiplication symbol, but it's the same as the X, the same as the dot. It means multiplication, right? So 1 plus 1 times 4 is the same as 1 plus 1 group of 4. Figure number 2, 1 plus 2 times 4 is the same as 1 plus 2 groups of 4. So figure 3, 1 plus 3 groups of 4, 3 times 4. So figure 10 is 1 plus 10 times 4, 1 plus 10 groups of 4. Figure 100, 1 plus 100 groups of 4, right? It's the same thing we did, but this time we're writing it sort of in symbols as opposed to words. So then what's changing here? When you look at this whole situation, what's changing?
The figure numbers.
The number.
And the group numbers.
So the figure numbers are changing here. Oh, sorry. Whoops.
The number of tiles.
The figure number is changing. All these numbers. And the number of tiles are changing.
Yes.
So it's the same, right? It's the figure number changes, the number of, and the number, I'm sorry, not number of tiles. I'm sorry, maybe I misunderstood. The total number of tiles, is that what you meant when you said the number of tiles is changing?
Yes.
Or did you mean the number of groups of 4?
The group.
The groups.
The group. But it's actually all 3 of those things are again changing. So it's the figure number, it's the number of groups, and it's the total number of tiles. As somebody said, it's exactly the same. All 3 of those things are changing, right? Okay. So then, what's staying the same?
The number of red tiles and the amount for the green tiles. The amount of green tiles doesn't change, and the 1 red tile.
So the number of green tiles, like we said here, is always 4. And it's always multiplication by 4. And then the 1 red tile is always there. So this is really the same as well, right? So 1 red tile and the 4 in each group is staying the same. Okay, so then we can move on to X, like for figure X, for any number, that's the figure number is X, right? And so now we're actually talking about figure. If you look at the top here, I made a small change. The figure number is X and the number of tiles is Y, right? Figure number X is whatever that number is. Y is what is the total number of tiles, right? Mm-hmm. So then how do we write an equation for this function?
Y is the total number of the tiles?
Yeah, in every case, right? 1 plus 1 times 4 is 5. 1 plus 2 times 4 is 9. 1 plus 3 times 4 is 13. That's the total number of tiles, right? This whole column, Y is the total number of tiles, yeah. So then, but now we want to generalize it to any situation. How do we write an expression or an equation for that?
Would it be 1 plus x times 4 equal y?
1 plus x times 4, yeah, follows this pattern. And then as an equation, just a little bit.
Y. Okay.
1 plus x times 4 equals y. Yeah. So any number you put in here, and then y is the output, the total number of tiles.
Y is the total number of tiles?
In this particular situation. Yeah.
Does it have to equal y?
Yes, because we don't know the variable for x. It can be any number. So y could be any answer, whatever number is the variable for x.
Okay.
So it's basically input and output. Basically, x is the input and y is the output.
Thank you. I was just about to write that. Thank you. Who said that?
Honey.
Thank you, honey. Yes, usually when you see x and y, x is the number you put in, y is the number that comes out.
Good to know.
So that in this case, if you know the figure number, you can figure out the total number of tiles. If you know x, you can figure out y.
So x is the variable, right?
Yes.
X and y are both variables.
Oh, okay.
They're both, because they both change, right?
Yeah.
Y changes, if x changes, y changes. Right? If x is 5, then y is, what is it? 5 times 4 plus 1. 21?
21.
Right? So y changes when x changes. Yeah, they're both variables. Okay. So this equation written in symbols is how you normally see it on tests, and you normally see it in math class, right? But it can also be written in words. 1 plus the figure number multiplied by 4 equals the number of tiles. Right? You take the figure number, you multiply it by 4, and then you add 1. That's the total number of tiles, right? This in words is perfectly fine. It makes sense. It works for any situation up to whatever number you put in there. You don't have to have this equation here. You don't have to have x and y. X and y and these symbols here were a choice that were made by mathematicians about 400 years ago. Before that, people used words to do algebra. Like algebra is an Arabic word, right? It comes from Islamic mathematicians in North Africa and the Middle East, right? They didn't have symbols like X and Y, but they did incredible algebra. They used words. I mean, obviously they didn't use English words, right? They spoke Arabic, but they used words. They didn't use symbols, but they did incredible math, right? More math than I'll ever understand. And our algebra is based on their math. But why would we want to use symbols here on the left instead of these words on the right? Why do you think we make a choice to write equations like this rather than doing all our math with words like this on the right?
I think
Sinai, are you speaking? I think maybe Sinai, are you speaking because you're muted?
I'm reading shorter.
Oh, okay. I'm sorry. Who is sharing? Does somebody want to try and answer the question?
To show a formula or a
so Cornelia said, yeah, to show a formula, to show a pattern, yeah. Any other reasons?
To make it shorter?
To make it shorter. I think that's a really big reason. Look at all these words.
Yeah. And right? Easy to understand.
This is actually, I mean, right, Leticia said it's easier to understand. It may not feel that way when you first start looking at this stuff, but eventually as you get more comfortable with algebra, this is easier to understand than these words. If you had to imagine all the math, like if you, I mean, you started doing all these different formulas, if it all was written out in words, it's so many steps, it's really hard to understand. It's actually a little easier to use to understand symbols. Once you understand what X and Y is, once you understand what variables are doing, it may not feel that way right now, but once you get practice with it, this is actually easier. It's faster. It's easier to write. It's easier to understand eventually. Okay. I think that's it for me right now. What I want to do for a minute, actually, it's not, you're not done with me, but I'm done with this part. I want to show you a new pattern. So give me one moment here. We're going to look at a new pattern today. Then you're going to have time in breakout groups to work on it.
Eric?
Yeah.
It's Kristen. I just wanted to say another reason that the equation is so good is it doesn't matter what language you speak, people can understand the equation.
That's a really good point, right? You have mathematicians and people collaborating and working together all across the world. It doesn't matter what language you speak. All mathematicians use those same numbers and same letters when they're doing algebra, usually, I think. Yeah, that's a really good point.